All right. Tell me how the chain rule assignment went. Easy? Man, you guys are getting so smart, right? I mean, does anybody have some problems on that they want to talk about? Eric, what you got?
I probably just because I've been juggling a lot of things.
Yeah.
So I haven't gotten around to watching some videos.
Sure.
I feel like whenever I do, get a grasp of the rules for these, I feel like it would be very easy to.
Yeah, I mean, it's just a pattern. Once you, if you're still catching up from being out, I mean, that's very reasonable. But yeah, absolutely. I mean, we just keep, it's this idea of how to apply when there's one function inside of another. And it's pretty straightforward once you get going with it. I don't think there was any huge deal. Now, here's the deal. You'll notice I haven't actually gotten your homework from you for a while. That's because I want one more day of kind of plowing forward with these derivatives and stuff like that. Because I think there will be some of them where once you do the stuff in section 3.7, actually you could finish up that 3.6 one, or you could fix some of those up, or some of the ones you weren't able to finish. I think actually it kind of goes together as a group. I think it makes more sense. Now, that being said, we did also have that you guys have seen in your email, right, that I sent you a snow day assignment. Because as far as I could tell, I hadn't given you that second one. And so let's go ahead. This is a good time to flex your muscles on those assignments, and get those kind of reviews or anything. It's a big long chapter. We want to have a chance to do it. So that's a good little assignment. I think it was 1 to 25 or something like that. I don't know. Something I copied out of another textbook. Yeah.
Which emails did you send?
I think I sent it just directly to everybody's EVSC email.
EVSC.
Yeah. Okay. But if you had any trouble getting it or whatever, just send me a message and I'll send it to you guys again. Okay.
Okay.
All right. Anyway, so it's just a scan of a review section of a different textbook. Okay. So they're just different problems than you've seen before. But I liked it because this set of problems at the back of that chapter didn't tell you, these are chain rule problems and these are product rule problems and stuff like that, because that is kind of a step. All right, so anyway, that stuff has to be in on Tuesday, and I'm going to also pick up all your or work with all your homework at that time, okay? But that was kind of my plan, was not to I think there's going to be situations where people will fill in on parts of the assignment they hadn't finished and stuff like that if I give them a little more time. All right, anywho. Now, today is not my favorite day in chapter 3. We're on 3.7. It says derivatives of inverse functions. This is by no means the most important thing we do in this chapter. But the book does it, and then it, in another chapter, goes back and talks about this again. So let's just real quick make sure we're remembering where we were with inverse functions. Remember, we had inverse functions back in chapter 1, I think. And it was just a notation here where we write the function and we have this -1 thing here next to it. That means the inverse function. It doesn't literally mean to the -1 power or something like that. The -1 there just means inverse. And so the inverse function of f is written f -1 thing here. All right. We actually had, on the first test, examples where you did inverse functions. And in case you don't remember them, which would be perfectly reasonable, let's do a quick review here. Remember, the trick was if you had some kind of function like y equals, 4x plus 8, there was a trick to finding its so-called inverse function. The inverse function, remember, was rearrange everything so that there's just x on one side. So in this case, we pull that 8 over to this side, and then we pull that 4 over to the other side. And then once you get to that point, the sort of magic trick that makes this work is you swap the x and the y. Swap this guy and this guy around, so that now you have y equals x over 4 minus 2. And this would then be the inverse function of this. Remember, the inverse function is the function that sort of cancels out what the first one did. So if we put, if we had f of x is 4x plus 8, the inverse function then, from what we just found right there, is x over 4 minus 2. And if you put this in for this x, they'll cancel each other out and you'll just get x. which is not so exciting. In fact, when we were doing this, there really wasn't that much we could do with inverse functions when they were just these little polynomial things. In fact, we don't really give much of a damn about these things at all, except in the context of some of those, what's the right word, transcendental functions like sine and cosine and log and things like that. Because those inverse functions can be darn useful for solving certain kinds of problems. Remember, like, we had functions like the inverse sine of 1/2. The inverse sine of 1/2 is the angle for which the sine is 1/2. That can be useful for those kinds of problems where, like, oh, we want to know, we've got a triangle here, maybe this is a building or something, and this side is 10 and this side is 20, and you want to know what this angle is. Okay, well, the sine of this angle right here is opposite over, not sine, how about tangent? That would be tangent. The tangent of this angle here is opposite over adjacent, or 1/2. Well, we could take the inverse tangent of both sides, and tangent and inverse tangent canceled out. So theta was just equal to the inverse tangent of 1/2, which is something you can get from like a calculator or something like that. So the trig ones of these were useful. In fact, that's what trig's doing right now, is these inverse trig functions. In the same sort of way, back in pre-calculus, we did the sort of thing with like natural log of x and e to the x, as one is the inverse function of the other. And remember, there were lots of applications of e to those exponentials, and ln, the natural log. There were zillions about growth rates and things like that. Here's the deal. Section 3.7 is going to spend way too much time talking about finding the derivative of an inverse function. And why? I mean, alright. Let's go back to our more algebraic looking example. Let's go back to that example where f of x, I think it was 4x minus 8. And that was the one, again, let's just do it real quick here. Let's find the inverse function. Y equals 4x minus 8. Let's pull that 8 over to this side. Let's pull that 4 over to this side. Do the old switcheroo right here and make this y equals x over 2, I'm sorry, x over 4 minus 2. So here is the inverse function, f inverse of x. Now, what this section of the chapter is doing is it's saying, let's find out what, here, let me get this y out of here. Let's find out what the derivative of this thing is. So like if you had this thing, the original function, given this thing, find the derivative of its inverse. Well, here's the deal. One whole exercise in how to do that would be just find the inverse and then take its derivative. I mean, Matt, what is the derivative of this thing? Of x over 4 minus 2? What's the derivative of that? You're overthinking it.
X with the...
What's the derivative of this?
X over 14, no, it's 16, maybe?
Nope. So there's just some number that we could rewrite this. Maybe it would be easier if I rewrote it this way. 1/4 x minus 2. What would its derivative be?
It'd be 1/4.
It's just 1/4. Yeah. So in this case right here, now the notation's kind of stupid. I mean, it's the inverse function of x, and then we're taking its derivative, so we'll put a little tick mark around there. I don't love that. But if you really had a problem that said, find the inverse, given this function, what's the derivative of its inverse? One way you could do it, maybe the even more common sense way to do it, would be to find the inverse and then take its derivative. And I've got no problem with that. But that is not what your book is going to do. They're not going to have you find the inverse and then take its derivative, except maybe as a way to check your answer. Rather, they prove the function inverse differentiation function or something. I don't remember what they called it. Hey, my computer went to sleep. Hold on. But they give you a rather ugly looking formula for this at the beginning of this chapter. Hey, computer, wake up. It's called the, where did it go? It's the inverse function theorem, and it's on page 300. And it's a mess the way they have it written. But if you look at, before page 300, on page 299, they have it written a little better. In fact, at the very bottom of 299, they have equation 319. And that turns out to be kind of our handiest way of writing this. Now, I don't want to write too far over that way because it doesn't show up on the computer screen. Let me write the formula out. So, again, I like it better on 299 than I do on page 300, where they're showing, in equation 319, they wrote it this way. Is equal to, alright, what are they saying here? They're saying the derivative of the inverse of f. See how that's what that's saying there? Inverse of f, and then its derivative. I don't like the notation, but we got to work with what we got. Is equal to, now again, if you look at page 299, number 319, 1 over the derivative of f, the inverse of f. Let me just make sure I've got that right. Okay, now, that looks like a mess. But make sure you have it in your notes, and I'll show you how you use it. Let's go back to our example that we had before. F of x was equal to 4x minus 8, and the inverse of that was equal to x over 4 minus 2. Now, so let's figure this out. How would we find given this function here, how would we find the derivative of its inverse? Apparently it is 1 over, alright, f prime. Alright, so f prime, this thing over here. F prime of this is, well, it's just 4, and then more stuff, but it's, I mean, f prime of, well, who cares? It's just 4. It's a constant function. And what was our answer? It was 4. I mean, 1/4 rather. Now, this is not the coolest example.
Wait, I thought you had to multiply it by the inverse.
No, it's not multiplied by the inverse. It is f of the inverse. So, like, this is the derivative of, like, we could put something in here, like x over 2. But f prime is just a constant function. It's just 4.
So we just put 1 over...
And then, so it's just that 4. Yeah. Let me show you one that works out more complicated.
So wait, we just put the derivative
Yep.
underneath 1.
We put the derivative under the 1, but then where the x was, we're going to put that f prime. I'm sorry, that f inverse. That one wasn't a great example because it's a constant. And so let me get one of the ones I did that is more complicated. That is more like the ones that are in this chapter. I did a bunch of these this morning. Where did I put them? Yeah. Okay. What if f of x had been x to the 1/3 power? Alright, I will save some time and energy and go ahead and tell you that in this case the inverse function is x cubed. Okay? You could do that whole business of computing an inverse function and figure that out. Okay? But for right now, let's say I gave that to you or whatever. Alright, the book is saying, given this, the original function, what's the derivative of its inverse? All right, the derivative of its inverse is going to be 1 over, it's the original function's derivative. What is the original function's derivative? Let's see, we take the exponent out in front, times x, and then we take this minus 1. 1/3 minus,
Negative 2/3.
is negative 2/3. Yeah, I just wanted to check over here what I was doing. All right, making sure I was not doing the problem right. So, this derivative of this is 1/3. Now, instead of x to the 2/3 power, negative 2/3 power, it is the f inverse. So it is, we plug in x, we plug in that x inverse function, that f inverse function. All right, and let's see, that's going to be 3 times, when we do that, we add multiply exponents, so that is 1 over x to the negative 2, which is equal to 3x squared. Hey, by the way, if we hadn't used this stupid formula that they gave us, we could have just said, let's just find the inverse of this thing. Oh, it's 3x squared, right? Wouldn't have been all that hard. Instead, the book made us say, fine, it's the derivative of f, which is 1/3 times x to the 2/3 power. But instead of x, let's plug in f inverse of x. So the f inverse was x cubed, and then we did all the math. Pause. Did you notice something happened that hadn't happened so far in this book? And that is, we had a power here that was not an integer. I could be wrong, but hasn't every time so far that you've used your power rule, it's been something like 3x to the 4th power, and then when you took a derivative, you brought that 4 out in front, and then you subtracted 1. Right? I think so far it's always been an integer, hasn't it? Your book takes this as an opportunity to show that it doesn't have to be an integer. It doesn't have to be anything in particular. It could be a decimal, a fraction, a negative number. I think there's one exception. I think it can't be a negative 1 or something like that. But we're not there yet. So 4 times x to the negative 1.5 power, its derivative is whatever 4 times negative 1.5 is times x to the negative 2.5 power. That is just fine. It turns out to prove that's true, you need this inverse function rule. So they wait to here to tell you that it doesn't have to be. But I'm guessing nobody freaked out when I did this derivative right here, right? If our function was x to the 1/3 power, we pulled the 1/3 out in front, times x, and we lowered this by 1, got negative 2/3. It's fine.
So what about like x to the power of log or x to the power of sine?
Don't even get me started. I'm sure some fine day we'll get to that.
X to the power of infinity.
Power of infinity? That sounds bad. Okay, so that was one reason why we did this. One reason is because, and I'm not going to work through that proof or whatever, but that business of using powers that aren't integers needed this rule to prove it. Whatever. I'm not that worried. Like I said, my guess is if I hadn't ever shown you that, you wouldn't have cared. You would have just assumed I could do it. You know, like if we wanted to do the derivative, if f of x is the square root of x, find its derivative. Well, it's important to remember square root is the same thing as x to the 1/2 power. So apparently the derivative of this will be 1/2 x to the negative 1/2 power. What does that negative mean on the exponent? 1 over? Yeah, so like, well no, the negative means it's 1 over, the 1/2 means it's the square root, so another way to write this would be like that. Okay. So one reason they took all this time to introduce this idea of using this rule to find the derivatives of inverse is because they wanted to prove this. That you don't have to have integers on those exponents to make this work. And again, that seems like it wasn't the best use of your time in that regard. The other reason, though, why they did it is because they want to be able to have derivatives of the inverse trig functions. The book wants to be able to say, what is the, like if f of x is equal to inverse sine of x, what is the derivative of this? We didn't do it. We didn't prove back in 3.4 or whatever section it was, there was the derivative of the trig functions. We didn't bother to go through the proof where we found out that the derivative of sine is cosine, and the derivative of cosine is negative sine, and the derivative of tangent is tangent squared, or whatever the hell. I always forget the one for tangent. And there's a proof for these guys too. The inverse tangent. And guess what? The proof for these guys involves this. I mean, what we're saying here basically is, we could be just saying the same question here. If we were given that the function was sine of x, what is the derivative of the inverse function? And this turns out to be the rule you have to use to prove that, to prove what it is. And you could see that you'd have to do this. You'd have to say 1 over, okay, it is the derivative of the outside, that's cosine, times the inverse function of this. And then there are rules, like back in trig, you learned, this is a familiar friend that the folks in trig were just learning about the other day. Except they're not really all that friend-like. But you can find out that they're all in there. Where are we at here? There they are. They're on page 304. It's a blue table labeled Theorem 313, the derivatives of the inverse trig functions. But you can work through them all and find out, for example, that the derivative of, like if your function was the sine of x, then the inverse sine of x, then the derivative of it turns out to be 1 over the square root of 1 minus x squared. Is that right? 1 minus x squared. Yeah. And there's one of those for inverse sine, inverse cosine, inverse tangent, inverse cotangent, inverse secant, and inverse cosecant. I'll be honest, we don't need to find the inverse tangent very often. Or inverse tangent maybe because it comes in those triangle problems. Inverse cosine, inverse cotangent, these are relatively rare things. Finding their derivative is even more rare. I'm kind of surprised the book took the time to hold a whole section on this. Not that it isn't hard, it's that it doesn't really get us all that far. Okay? But that's okay. Do you need to know how to do those proofs? No, you do not. Am I going to make you do problems that have inverse signs and so on? Sure. But you have now on this table on page 304 or whatever, the derivatives of the inverse trig functions. You can use that. Okay? So like if you've got some problem, here, allow me to do a problem. Look at me erasing that equation that we have up there on the board that is the inverse derivative for whatever function thing for the beginning of this chapter. So if you have some problem where like f of x equals 3x squared times the inverse sine of x, here's the deal. Hey, let's use our big brains. What kind of problem is this that I have written up there on the board? Is that a power rule problem? Is that a quotient rule problem? Is that a product rule problem? Is that a chain rule problem? What do we got here? I think this one is a product rule, right? We've got two things. Here's a thing, and here's another thing. And so if we're trying to find the derivative of this, remember it'll be the derivative of the first. Actually, this thing right here is not so hard at all. 6x is its derivative, times the second, plus the first, times the derivative of the second, which I'll write right now as the derivative of the second. Now, you've got a derivative of an inverse sine in there. I suppose the pain in the ass textbook would like for you to do that derivative of that sine using our new nifty equation we learned at the front of the book, at the front of the chapter, but I don't care. I'm happy if you go to page 304 and look up that this term is whatever it is. It's 1 over the square root of 1 minus x squared, I think. So if you got as far as saying my answer is 6x times the sine of the inverse sine of x plus 3x squared over the square root of 1 minus x squared, I'd be pretty happy. And you didn't really have to do that in the front of the chapter. In the same way, all these kind of ones that you've got going on that are, these simple little linear expressions, there's going to be problems in there. They're like y equals 3x plus 4, and then they want you to find, okay, so instead of y, let's call it f of x, just to be more consistent. Then find the inverse function's derivative. And they're going to want you to use that function at the front of the book, at the front of the chapter. But honestly, I don't care. If you want to just find the inverse function and then take its derivative without using that theorem, I'm fine with that. Okay. So, what am I really saying? I'm saying we're basically using this section as a way to bring us to A, permission to work with exponents that aren't integers. Because we didn't really need permission. We would have trusted that it was going to work, but whatever. And, hooray, we now have derivatives of the inverse trig functions if we want it. And again, we could be proving it using that theorem at the front of this section, but we're not going to prove that. That is not the most important thing we're doing. All right, so that being said, you now have an assignment about this stuff. Let's look at the list here. Where did it go? On Drive. On Finding Calculus. All right, so this comes from the end of this section. It is page 306. Page 306, I want you to do numbers 269 through 287I. And don't forget, there is that snow day assignment. And this is all due on Tuesday. On Tuesday, I also will round up then all your assignments and give you guys grades on that stuff. Okay?
Scoliosis.
Okay. All right. Well, then let me go ahead and stop the recorder, and we'll work on the assignments.